Hello, everyone. Thank you for your interest in our research poster. My name is Dr. Derek Manheim, and I'm supported by my colleagues, Dr. Marissa Matzler, Dr. Nasli Yesler, Dr. James Hansen, and Dr. Jiong Choi, who assisted me with this research. We are currently working under the Sustainable Materials Management Extreme Events Reconnaissance, or SAMIR for short, organization, which is dedicated to researching new and innovative approaches to sustainably manage post-disaster waste materials. Our research poster today is entitled Integrating Social Equity in a Sustainable Post-Disaster Materials Management Decision Support Framework. Let's zoom in here. All right, catastrophic natural disaster events generate a significant quantity of debris and waste materials. As disaster events continue to intensify and frequently occur as a result of global climate change, there are magnifying yet disproportional debris and waste material impacts exerted on the livelihoods and the well-being of low-income and minority communities. The immediate generation of such large quantities of these materials typically overwhelms waste management authorities, as they must ensure safe, rapid, and reliable material removal, storage, and processing from the community that is affected. However, current disaster waste management strategies in the US are not sustainable. Much of the waste that is generated from these events is sent directly to solid waste landfills. This is due in very part to limited research quantifying the feasibility of post-disaster waste materials recovery, recycling, and reuse. A major factor limiting the recovery, recycling, and reuse potential of these materials is the general lack of knowledge of the human health, the environmental impacts, and the social equity concerns associated with these materials. Before these materials can be effectively utilized as a resource, under the triple bottom line, these factors must be carefully examined and or predicted to assist local, state, and federal government authorities when planning for and responding to waste generated from natural disasters. So the overarching objective of this research is to develop a quantitative decision support framework that assists waste management authorities at various levels to integrate and adopt sustainable waste management policies and practices. We expect that this decision support framework will be very valuable for both pre-disaster planning and post-disaster response and recovery phases. By conducting this research, we set out to achieve three specific advancements. First, we would like to predict human health and environmental impacts and risks associated with the post-disaster materials themselves. Second, we plan to integrate social justice metrics on the census tract level to quantify the vulnerable demographics and pollution burdens of the affected communities. Third, we would like to incorporate a spatial scale in addition to the conventional temporal scale of analysis to account for spatio-temporal variations in the waste material and the community-specific safety and equity metrics following a natural disaster. Now, to apply this decision support framework, we have selected a representative disaster event, Hurricane Laura, to focus on. Hurricane Laura took place on August 27, 2020. It made landfall as an intense Category 4 storm near Cameron, Louisiana, and it tied the last island hurricane of 1856 as one of the strongest landfalling hurricanes in Louisiana state history. High wind speeds and storm surge resulted in substantial impacts to the residential and commercial sectors throughout Louisiana. Overall, approximately 1.5 million people were affected from Texas to Louisiana. A total of 32 fatalities were reported for this event. The total economic losses range from $4 to $12 billion, depending on different estimates. In a previous virtual assessment report conducted by SAMIR, we have estimated the total debris generation using HAZUS MH to be on the order of 12 million tons, which is significantly larger than the total debris reported from debris clearance right-of-way reports published by the Department of Transportation. This debris estimate afforded by HAZUS includes wood, masonry, steel, and concrete structural components, along with vegetative tree-borne debris associated across residential, commercial, industrial, and institutional infrastructural sectors. As observed in this figure here, the urban community of Lake Charles, which is the focus of this study here, lie directly in the category 4 hurricane path, resulting in some of the largest debris estimates across all parishes that were examined. This region of Louisiana is also recognized as a socially diverse region with significant differences in economic standing, race, and ethnicity observed compared to the national census level. Okay, moving on to methodology. This post-disaster materials management decision support framework relies on 4 primary and successive modeling steps that integrate a wide array of existing tools and databases, as shown in this figure. The first step is to construct the detailed building inventory of the community of interest. In this example, we have used the data sets generated by this Structural Extreme Events Reconnaissance Organization under Project 3207 that is currently available to download from Design Safe. This data set contains asset level detailed reconstructions of around 26,000 residential buildings in the Lake Charles region. This inventory was generated using the building recognition using AI at large scale, or Braille's for short, city builder application available within SimCenter on Design Safe. Next, the data damage states and the corresponding debris generation from the building inventory was simulated. Wind and water penetration damage and corresponding loss estimations for each building was performed using the hurricane module available within the Regional Resilience Determination Tool, or R2D, that's hosted again on SimCenter within the Design Safe website. The damage states attained for each building from the Pelican module that's available in R2D were then separately translated to debris tonnages in MATLAB using predefined hazardous debris generation functions. As part of step 2, the demographic profile and housing inventories are simulated in the Lake Charles region using existing modeling platforms available from the US EPA under the Human Exposure Modeling Framework. This step was very critical to obtain a reliable representation of the interior building components, products, and associated materials that could potentially chemically contaminate the debris following a natural disaster. In this framework, first, the Residential Population Generator module, or RPGen, available within the Human Exposure Model, was applied to generate a realistic synthetic population of individuals within the Lake Charles community. This synthetic population data obtained from RPGen outputs assist in the prediction of whether certain individuals within a household will use different products or materials, and also provides information as to whether certain contamination-causing building components, such as TVs, electronics, and other appliances, may be present in each household. Households were generated from RPGen were then matched to the SimCenter building inventory results on the basis of the year built, the income standing, the inhabitants, the number of stories of the building, the presence or absence of a garage, and the occupancy class, whether it was a Res 1 or Res 3 multi-family dwelling residence. This data is then used as input to the product use scheduler module within HEM, the Human Exposure Model, which generates household-specific, member-specific product and material use diaries. These diaries contain detailed information on the product or material consumption patterns, including the quantities of each material and the associated chemicals contained in each of these materials, as well as the frequency of use of these materials over a simulated 1-year time period. This analysis was constrained by applying the American Community Survey results in the designated census tracts of Lake Charles. For each census tract, the community survey data was used to identify the number of households of a given race and or an ethnicity, thereby establishing a racially and ethnically representative simulation basis. Step 3 involves the determination of the risk and the social equity matrix associated with the post-disaster waste materials. A previously developed quantitative risk classification framework was adapted to evaluate the human health and environmental impacts of the post-disaster waste materials. The human health component of this classification framework is based on ranking the individual chemical quantities the exposure frequency to these chemicals, as well as the distinct hazard classes these chemicals pose to human health on a scale of 1 to 5. Here, 1 represents no risk and 5 represents extremely high risk. Chemical quantities and frequencies of chemical exposure are based on household-specific product material use diary outputs from the product use scheduler module, and hazard classes are based on an evaluation of over 21 distinct human toxicity pathways using the Chemical Hazard and Assessment database. Based on the rankings obtained from these different classifications, an overall risk score is calculated that evaluates the potential human health risk of the generated materials on a household-specific basis. A similar approach is applied to estimate the environmental impact risk score. However, the environmental impact score is based on 4 distinct ecotoxicity metrics available within the Chemical Hazard and Assessment database, and is partitioned into 3 individual compartments: the air, soil, and water compartments, based on the chemical-specific transfer coefficients. Transfer coefficients are representative physical or chemical properties, such as octanol air or octanol water partition coefficients, that indicate the likelihood of a chemical to transfer from the product state to the environmental compartment of interest. Chemical-specific transfer coefficients were obtained from physical chemical property predictions available from the US EPA's COMTOX chemical dashboard. Social equity scores were based on 2 cumulative metrics: integrated population burdens and vulnerable population characteristics. To calculate these metrics, US EPA's EJ screen tool was used to obtain census level information covering socioeconomic factors, including unemployment, minority percentages, education and economic standing, environmental pollution exposure metrics, including potential lead paint, cancer risk, ozone, and particulate matter concentrations in the air, as well as environmental effects, including the proximity of these communities to cleanup sites, Superfund sites, solid waste management sites, and wastewater treatment plants. And finally, the vulnerable population data included metrics covering the percentage of the population that are children versus those that are elderly, asthmatics, as well as those people that suffer from heart disease. The pollution burden and vulnerable population metrics were then multiplied to estimate the corresponding social equity score of each household. Lastly, step 4 involves modeling of the waste material management operations following the disaster event. Since the previous risk scores are not expected to vary much with time, only the debris quantity generated and remaining at each household varies temporally. The weighted average of the scores is then applied to calculate the overall post-disaster material prioritization score, or in this case, MPSI. And again, each score is generated for all households simulated within the community of interest. All weights are maintained equal in this equation so as to not bias one potential risk score over the other during the waste management life cycle. In summary here, higher computed MPS values, or near 1, indicate greater priority for material removal and management. Given the MPS score, the disaster waste materials operation tool developed by Glorka et al. And modified in this application is then applied to optimize the debris operations and management. This tool directly integrates geospatial information of solid waste landfill, recycling and reuse centers, and temporary debris storage or processing locations, as well as their capacities, to provide a realistic framework for estimating the time, effort, and resources required to sustainably manage post-disaster waste materials. Using this tool, a set of 3 bounding low, medium, high uncertainty scenarios can be run and compiled to provide an adequate factor of safety to ensure that human safety, health, environmental health, and social equity concerns are equally and reliably addressed when managing the post-disaster waste. Now moving on to the results of discussion. In total, for the Lake Charles community, we have evaluated over 20 census tracts, 25,850 individual residences, around 320 household products and materials, as well as 1,000 corresponding chemicals linked to the household products and materials. As observed in the figure here, the results indicate that social equity scores are highest in magnitude across all census tracts, but also associated with the greatest variability. These results suggest that social equity scores contribute greatly towards our preliminary understanding of the social vulnerability to the multifaceted hazards posed by post-disaster waste materials. However, these estimates must be refined on a more specific asset level of analysis to dampen the variability observed across all census tracts and to be more comparable to the other existing sustainability metrics here. Lastly, it's important to mention that integration of social equity scores provides an indirect indication as to the susceptibility of different communities to natural hazards induced damage of nearby industrial facilities, waste management infrastructure such as landfills or wastewater treatment plants, as well as hazardous waste sites. Damage to these facilities provides another route to chemically contaminate the post-disaster waste materials, aside from the typical household-specific components, products, and materials analyzed here. All right. In the next figure, I presented the results of the decision support framework across 4 priority census blocks within the community of Lake Charles that were most affected by Hurricane Laura. In panels A and B, I'm comparing the isolated normalized debris quantity scores and the integrated human health, environmental impact, social equity, and debris quantity scores using the more advanced MPSI value. Both approaches are presented on identical scales between 0 to 1 for fair comparison. For reference, the path of the hurricane is to the direct left or west of each panel. As observed in the figure, the DQSI scores tend to pinpoint the individual structures that have suffered the greatest damage and losses. However, the MPSI scores provide a broad and regularized visual comparison of the combined human health, environmental impact, social equity concerns, and physical damage and losses following the hurricane. Therefore, the MPSI analysis facilitates identification and prioritization of large spatial scales for safe, rapid, and equitable waste management here. Ultimately, this decision support framework will offer the capacity for waste management authorities to develop, compare, and optimize strategies to reduce the spatio-temporal extent of the waste material impacts and enhance recycling and recovery rates of these materials. Finally, I've included some preliminary analysis as to what specific chemicals and products or materials are contributing most to the overall human risk and environmental impact scores for the community of Lake Charles. Across all households and census tracts, citronellol and ethanol contributed most to the human health risk score and environmental impact scores, respectively. Citronellol is not to be confused with citronellol, which is significantly less toxic. Citronellol is a suspected human carcinogen and bodily irritant. Ethanol has a high chronic aquatic toxicity. The main products and materials contributing to the human health risk scores and environmental impact scores were fabric treatment and dye products commonly used in laundry and arts and crafts applications within the household, as well as aerosolized insecticide products such as foggers or bug bomb sprays. All right, heading into conclusions and future directions. We have aligned the overall goal and scope of this decision to support framework with some preliminary qualitative analysis of case study interviews with representative waste management authorities. Common testimony has indicated that many local waste managers are often confused as to if, when, where they will require assistance from state or federal authorities during the response and recovery efforts. The outcomes from this decision support framework will identify where and to what extent social equity concerns, environmental impacts, and human health risk associated with these waste materials are most egregious to both prioritize and streamline waste management efforts. This framework is then expected to be applied during pre-disaster planning as well as post-disaster response and recovery. By using this framework, waste management authorities are able to develop, compare, and optimize waste operation scenarios that enhance recycling and reuse of the generated materials and result in the lowest aggregated impact on human health and the environment. Integration of social equity scores into this framework ensures that the waste management operations are mutually beneficial and inclusive for all community members, regardless of their race, ethnicity, or social standing. Future work on this topic will further develop the temporal modeling component of this framework, i.e. step 4, provide a more realistic chemical dose response human exposure modeling assessment, and introduce quantitative sustainability resiliency analysis as a tool to merge sustainability and resiliency thinking principles into post-disaster waste management systems. With that, I would like to acknowledge funding for this research that was provided by the National Science Foundation, EAGER grant number 2014330, which has established the Samir organization. If you have any questions, please feel free to type in a message below or contact me directly at the email provided. Thank you for listening.